pick up where we left off. One thing I wanted to show, but it was a figure not in line with the chapter we're reading. In this figure, I tried to show you how the alkyl groups work. So they're attached to a big molecule, what is called a molecule Fred. Could be anything. So here would be methyl, that's ethyl. Here's what the skeletal structure would look like. Isopropyl, butyl, the other ones. And so just to give you an idea, so if this molecule was named Fred, that was its real name, then you could call this an ethyl Fred, and a 1, 2, 3, 4 total, so that's butyl. And it's split on the end, so it's isobutyl. So ethyl isobutyl Fred. Just to give you an idea how the alkyl groups work. But I should have covered that previously, because we were starting the chemical properties already. Like I was saying, all the chemical properties are numbered as chemical reactions. Sorry to make you dizzy here. Oh, okay, so we did aliphatic substitution. So we should be doing ring opening right now. So anyway, ring opening reactions happen because of bond angle strain. So if I take cyclopropane right here, the bond angles are 60 degrees. There's 180 degrees in a triangle, 3 angles, so 60 degrees each. And what does carbon really want to be? 109.5 degrees. So each carbon right here is under ring strain, and that can cause it to be to go open. So I'm going to show you what I mean by that. So here is cyclopentane. I'm going to make cyclopropane. That's 3 carbons in a row. I'm going to have to make it into a cyclic form. If you look at the model, when it's relaxed, it's trying to do 109.5 degrees, right? So you can see that what I have to do is really twist this a lot to make these two bonds line up. So, you know, we really should be wearing eye protection when we're trying to do this with these models, because you really have to turn these pretty hard. I mean, the only reason I can do that is because, you know, I practiced in the woods for 20 years under the supervisor of my senseis, right? But you can see how the bonds are just contorted right there. So the safest place for electrons to be is exactly in between the two atoms that they're bonded with, okay? When you put them out of plane like that, they're susceptible to other things in the environment. They're under strain, so, you know, just bumping into things could occasionally cause one of these to break. So if I put something like bromine in there, that's enough to make some of these break. So the bromine is breaking this bond right here. So notice that one carbon needs another bond, right? Excuse me, I gotta put this back on. So when I open this up, this carbon needs another bond, so does this one. So the two things that are breaking the bond go on the external carbons. What if I have cyclobutane? Okay, so now I got 4 in a row, and I got to make it into a cyclic form. can see that they're still not very well connected, right? I'm going to have to push these into the same plane to get them to connect. It's not as bad as doing cyclopropane, but it still, you know, takes an effort to put it in there. Believe me, I make it look easy. You can see the bonds are still a little bit distorted, right? So there's a ring strain here. The bond angles in a square are 90 degrees. It wants to be 109.5. So if I do get something in there that will break this, then one entity needs to go here and another one needs to go here. That's how I would get the bromines on the two external carbons. Then, if I make cyclopentane, it's pretty easy to get this thing to go together. See how that just goes right in there? Quite easy. So the bond angles are 108, which is not that far away from 109.5. So this is actually not too bad. These do not normally undergo ring opening reactions like cyclopropane and cyclobutane. Part of the reason is you see that you get a little bit of play in here where they can relax a little bit. And then if I add one more, I get cyclohexane. And you see the cyclohexane ring is not flat, it's puckered. It can do this. That lets every single carbon atom in there relax into 109.5 degrees. So this is stable. And 5 and 6 member rings are quite common in biology. And so therefore, organic chemists spend a lot of time doing conformational considerations about this. I don't think it's important. Really, right now, in some cases, it does become important when you're looking at chemical reactivities. But in organic chemistry, we're doing synthesis. It can be important, but we're not going to do that. So here's the two most common, how do you say, conformations. So if I go to the opposite side carbons, if I push them both up, this is called the boat form. See, it's like a little boat, right? And if I take the two carbons opposite from one another, I put one up and one down, this is called the chair form. And the chair form is much more stable. Here's the reason why. If I put it into the boat form, you can see that these two entities, whatever is going to be bonded to them, are going to be trying to occupy the same space, known as steric hindrance, steric interference. So the good thing to remember or learn about this conformations is that in general, the chair form is much more stable than the boat form. Oftentimes we write them in three-dimensional ways on a two-dimensional surface. I'm not going to ask you to do that, but you can see that there's an equilibrium over here. It's not a chemical equilibrium, it's a conformational equilibrium. So here is the boat form. No, I shouldn't say that. Here's the boat form, here's the chair form, right? But now it gets important considerations when you start putting other atoms on there. Say I take some big things and put them right here. So those big things in the chair conformation are right in each other's way. That's not going to happen. So this is almost prohibited, where this would be okay. So then we would say that this particular ring, because of its substituents, is locked into the chair form. But if I were to take this and put it over here, then, you know, the boat form is not too bad. The chair form is still better, but see what I'm getting at? But we don't really care about this. I just need you to know that there is a equilibrium between the different kinds of conformations, and the conformation is important. So any questions about that? Okay. So naming alkenes, these have double bonds and geometric isomers. So you name them just like alkanes, except the numbering system is set by the position of the double bond. You're going to name this as an alkene. So the alkene is taking dominance over how you name the molecule. So that means that I have to find the longest continuous chain that includes the double bond. So it's going to be 1, 2, 3, 4, 5, no matter what I do. So the root name is not pentane, but pentene. And then, where do I say the double bond is? It could be at carbon number 1, 2, 3, 4, or I first encounter it at carbon number 1. So you should know by now that we go by the lowest numbering system, right? But in this case, it applies to where the double bond is because it's an alkene. So that means that this is carbon number 1. So this right here is named by 1 pentene. 2 pentene, the double bond would be here. So then there's the longest continuous chain. What are the substituents that are on that longest continuous chain? Here's a methyl group, another methyl group. So it's dimethyl. Where are they? 1, 2, 3, 4. They're both on carbon 4. So 4,4 dimethyl, 1 pentene. And notice that every substituent, even if it's the same, gets a number. If I were to see the name 4-dimethyl 1-pentene, I'm like, well, I don't know what that is. Somebody made a mistake. I can't trust it to be 4,4. And here's an alternative method of giving the number for an alkene. Either one is fine with me. So then, geometric isomers arise because you do not have free rotation about the double bond. So notice that in the cyclic forms, I can't simply put this anywhere I want. It's locked. I don't have free rotation about that bond in a cyclic compound. And when we look at double bonds, it's the same thing. Excuse me, playing with models. So here's a double bond. If these are carbons, this would be 1, 2, 3, 4 in a row. So this would be butene. First encountered at carbon number 2, so 2-butene. These would be hydrogens, right? But notice that the model is made so that I cannot rotate this freely. To rotate it, I would have to break a bond and then do the rotation and then reform the bond in a different place. That's a chemical reaction. Okay. So that means that this have these made. So anyway, just imagine that this one here is not the same as this one here. So when I'm naming this compound, this is 1, 2, 3, 4 in a row, so it's 2-butene, right? But this compound was different than the one I just had. They're different by their shape. So then how are we going to explain that? Well, we can use the EZ configurations, which they mostly do in organic chemistry. But for us, we'll just stick with the old-fashioned way of cis and trans. So this one, this is what we do. You look at one atom in the double bond, and you say, here's the big one, here's the small one. Then I look at the other carbon, here's the big one, here's the small one. If the big ones are on the same side, it's called cis. So this is called cis-2-butene. If I did a chemical reaction, man, these things can be hard. It's still 2-butene, but now this is trans. So I look at this carbon, the big one's down. I look at this carbon, the big one's up. They're opposite to each other. They're trans to each other. So we call this trans 2-butene. So how would we name this compound? 1, 2, 3, 4, 5, 6 in a row, so it's hexene. Where is the double bond? 1, 2, 3, or 1, 2, 3. So no matter which way you go, it's going to be 3-hexene. So then, what else is there? So here's 3-hexene. There's a methyl here and a methyl here. So it's dimethyl, and carbon number 1, 2, 3, and 4. So it's 3,4-dimethyl 3-hexene. But now I look at this carbon, and I see the biggest one is here. I look at that carbon, the biggest one is here. And so because the big ones are trans to each other, they're opposite, then we say it's trans. And what would the cis look like? This would be the cis. Make sense? And what about this one? Watch this one right here. What I'm going to do is do another chemical reaction. So now it's got a completely different name, doesn't it? It's 1, 2, 3, so it's now propene. 1 propene would be this. So this is on the number 2 carbon, right? So 2-methyl, I'm sorry, 1 propene. 2-methyl, 1 propene. And I go to this carbon, and look, these two are the same. So are these over here. If any of them are the same, then you don't have an EZ and you don't have a cis-trans. There's no geometric isomer. So if I'm looking at this one right here, the longest continuous chain is 1, 2, 3, 4, 5, 6. So it's hexene. The lowest number for the double bond would be number 2. So it's 2-hexene, takes care of all of that. And then I have a methyl and a methyl. So it's dimethyl on carbon number 2 and 3. So 2,3-dimethyl 2-hexene. And then I look to see if there's geometric isomers. So I'm looking at this carbon. Here's the big one. Here's the small one. I go to this carbon. There is no big or small. So therefore, there is no geometric isomers. And I will go through the EZ convention because it is more precise. So what you do is not simply which one is bigger and which one is smaller. You have to go through a priority system. So to decide who the winner is that's attached to this carbon, you go to the very first atom that it's bonded to. That's a carbon, that's a carbon, okay? That's a tie. This carbon then goes to a hydrogen. This carbon then goes to a carbon. So a carbon is bigger, more important than the hydrogen, so this one wins. Make sense? So this gets the priority here. Then I'm looking at this one. Here's a carbon to a carbon, so nobody wins. Here's a carbon to a hydrogen, but then a carbon to a, carbon to a carbon, and here's a carbon to a hydrogen. So this one wins. So now because the two winners are on the opposite side, it's called E, okay? If they're on the same side, it's called Z. And the way I always remember it is that, well, these are Z same. Stupid, but works for me. Okay. So here's the reason why it's a more precise system. If you look at something like this, you're going carbon and bromine. Now, which one is bigger? Which one gets the priority? Well, bromine is a much bigger atom than is carbon. See how that works? So the EZ system is more precise. We're really not going to use it much, though. So the trans and the E geometric isomers are slightly more stable because they have less steric hindrance. So remember, it is a chemical reaction to convert the trans into the cis and vice versa. But here is the cis, here's the activation energy, and if it comes back down and forms the trans is slightly lower energy. Okay. Here's some biological significance in geometric isomers. The naturally occurring oils contain cis double bonds. Overheating cooking oils can convert some into the more stable trans configuration. Why is that? Because there's less steric hindrance, right? So nature tends to make all cis, but if you heat it up, in other words, supply this energy of activation, then some are going to come back down this way, and when they do, they're more stable. So this is the preferred more stable isomer in chemistry, but that's different than what you find in biology. So trans fatty acids have been shown to have negative effects on the immune system. And if you look at large restaurant chains, they have the resources to fix that chemical reaction. In other words, they can change frying oils much more often. Smaller restaurants, they're scraping by. They may not have the ability to mitigate the production of trans fatty acids. And then the visual pigment retinol. It comes from beta carotene. So I don't think I have a structure of beta carotene here, but beta carotene comes from carrots. And if you cut it in half and you oxidize one of the ends all the way to an aldehyde, then that would be called a retinal. Anyway, so here's what happens. If I change from a cis to a trans, right? How much of a degree change is that? I'm looking at this bond angle and I care about this part right here. If I change this part up to like this, that's a 120 degree change in direction of the chain. So what happens is that light energy is used to break that cis bond. It forms back into the trans, And that causes a 120-degree change in the bond angle. So light energy is able to do a physical change, and that physical change is basically what activates the optic nerve. So here's vitamin A, which is called a retinol because that's an alcohol. There's an enzyme that takes the primary alcohol and oxidizes it one step into an aldehyde. Now that's called retinal. And notice that it's called all trans. So then what happens to happen? It gets converted into the 11-cis. And then it binds with this protein, this visual protein called opsin. So now it's ready to actually, what's the word for it? Activate the optic nerve. So notice that we have double, single, double, single, double, single, double, single. That's called a conjugated system. Conjugated systems are really good at absorbing light energy. So the electromagnetic radiation is absorbed by the electrons in these pi bonds. When the electrons become more activated, they have more kinetic energy, they're more likely to undergo a chemical reaction. So that's what it does. So then the 11-cis gets converted into 11-trans. Well, now it's done its job. It really can't do much more. So what you have to do is recycle this to turn it back into the cis again. So it has to be cleaved off of the visual protein opsin, right? It's removed in the trans form. It has to go to an enzyme that is basically in the liver, and then it gets converted back into the cis. Then it goes back to the eye again, be converted into rhodopsin, and now it can be able to react to light again. So now that you know this mechanism, and you know that the liver is involved here, you think liver disease has anything to do with vision? Are they related? What about circulatory diseases? They're all related, aren't they? Your body is a system, and every part of the system has to work well. Otherwise, your body's not working so well. Anybody have any questions? Okay, so terpenes are kind of interesting. So there's a whole bunch of plant terpenes. And it's kind of interesting because, plants are all kind of related to each other. And there's a lot of molecules that we call terpenoids. So what are terpenes made out of? They're made out of isoprene. Isoprene is 2-methyl-1,3-butadiene. So here is isoprene. Let's analyze this name. Notice I got 2 double bonds here. So I'm going to name this as a diene, di meaning 2. So that means that both functional groups have to be in the continuous chain. So 1, 2, 3, 4, so butane, diene. And where are the double bonds? Carbon number 1, and then carbon number 3. So 1,3-butadiene. This is a methyl group. And so it could be at carbon number 2, or it could be 1, 2, 3. So the lowest number would be 2. So 2-methyl-1,3-butadiene. And notice that there is a single bond right here in the middle. So you can rotate this right there. And let me just see how this works. I'm going to play with my iPad here. So you have free rotation about this single bond right here. So when I draw it this way, it looks like maybe a little pony or something, right? Or a dog or something like that. Let's see, now where'd this go? So I have a colleague, I haven't seen her in a couple of years. She was from Italy. So an Italian PhD. And we were talking one time, and we were talking about isoprene for some reason. And I said, yeah, I always remember it as a little horsey. And she says, yeah, me too. All the way from a different country. But anyway, these things can be joined together, either head to tail or tail to tail. So you can have all kinds of different molecules built together by this one basic unit. But every terpene will have 1, 2, 3, 4, 5 units as the carbon. So it will have 10 carbons or 15 or 20. It would never have 21. Okay? So how do we name dienes and trienes? So you use the name diene or triene. And we seem to omit the NE. So what does that mean? 1,3-butane diene becomes 1,3-butadiene. Or you could say buta-1,3-diene. So if you write on a test or something, 1,3-butane diene, I'll probably go, they didn't know to leave off the NE. Is it something that you're going to go to jail for? No. Uh-oh, what's that? So as long as you write a name that adequately describes the molecule, that's what I'm looking for. Okay? I'm not looking for the grammar. If you say just ene, then that's a problem because you left out something that's important for the molecule. And the longest chain must include all the double bonds, right? So if I look at this one right here, what's the longest chain? 1, 2, 3, 4, 5, 6, 7, 8. Or 1, 2, 3, 4, 5. Wait a minute. What do I do here? I have to include both the double bonds because I'm going to name this as a diene. So in this case, I'm not using the longest continuous chain. So that this becomes an alkyl group, substituent. I got 1, 2, 3, 4, 5, 6 in a row. So it's hexane, hexadiene, and where are the double bonds? The choices are 1, 2, 3, 1, 2, 3, 4, 5. So 1, 5, or 1, 2, 3, 4, 5, 6. So why did I choose here 1, 5 instead of 1, 6? Because I want to give this substituent the lowest possible number as well. So if I would have done a 1, 6, then this would have been 4. See that? So I started here, 1, 2, 3, 4, 5. That makes this carbon number 3, where it has the butyl group.
I have a question.
Sure.
The terpene portion just up above. So is that molecule, is that a diene or a terpene or a isoprene? I'm a little bit confused on that.
It's all of them. So the monomer, its common name is isoprene. Here's its systematic name, right? And just by itself, it's simply called isoprene. But if I start putting it together and building larger molecules, those larger molecules are called terpenes. That makes sense?
Okay, yeah, that does. So a diene is just any time it has two double bonds.
Exactly, right.
Okay.
Yeah. Okay, what about cyclic alkenes? So it's kind of understood that cycloalkenes are going to be cis. It would be kind of a cruel joke to give you some models and tell me to build the trans form of this, because it's just not going to work. You know what I mean? So the interesting thing about this is that you have to number through the double bond. That means that the two carbons in the double bond are going to be named or numbered 1 and 2. Okay? So here's my choices: 1, 2, 3, 4, 5, 6, 7, 8. Or 1, 2, 3. So I'm going to go this way to get the lowest numbering system. So if I say cyclooctene, I simply would draw this, right? And then if it's 3 isopropyl, where do I put the isopropyl group? 1, 2, 3, it would be here, or 1, 2, 3, it could go there. Does that make sense? And then the substituents can still be cis or trans. So here is 1, 2, 3, 4, 5, right? So cyclopentene. And if I didn't have any substituents, I wouldn't have to say it's 1 cyclopentene. It would just be cyclopentene. But I do have substituents, so I have to give them the lowest numbering system. So 1, 2, 3, 4. In this case, it would be 3,4-dimethyl. If I went this way, 1, 2, 3, 4, 5, it would be 4,5-dimethyl. So the simplest, lowest numbering system would be counterclockwise in this case. But then the way it's drawn, this is coming into your face, that's going away from your face. So they're going in opposite direction, so that means it's trans. Same thing for here. Okay. Well, what about alkynes? Similar to alkenes, but we don't have geometric isomers. So the longest continuous chain has to include the triple bond. So 1, 2, 3, 4, 5. So that would be called pentyne. And then where do we first encounter the triple bond? On carbon number 1. So the root name is 1-pentyne. We see that it's dimethyl. And where are the methyls? 1, 2, 3, 4. So 4,4-dimethyl 1-pentyne. Okay. And so here's another one. Again, this has to be in the longest continuous chain, right? So you should probably work that one out on your own. So the physical properties of alkenes and alkynes, they're similar to all the other hydrocarbons because there is no polar bonds. The bond angles in alkenes are 120 and in alkynes are 180. And conjugated alkenes absorb light. Many of them are highly colored. They also are more reactive. So here's an example. Para-aminobenzoic acid, PABA. It was used as a sunblock. And suntan lotions were, no, not suntan, but sunblock. Which, by the way, when I was a kid, we didn't have any of those. So there's pictures of me as a baby down at the beach and just sitting there in the sun. Nobody really knew that ultraviolet radiation was causing skin damage and possible, melanomas. But why could it act as a sunblock? Notice that it's double, single, double, single, double, single, double, single. It's a conjugated system. So these pi electrons in the double bonds are able to absorb energy from the light and convert that energy into heat because of the kinetic motion of the electrons. Beta carotene, which if you cut it in half and oxidize it, you start to get visual pigments, right? Vitamin A. So look at beta carotene. Why is it orange? Because look at this huge conjugated system. So you're looking at a carrot, you're looking at the beta carotene, it appears orange. Why is it orange? Does that mean that the beta carotene is actually orange? No, what it means is the beta carotene is absorbing all wavelengths of the visible light except for the orange. The orange is not absorbed, it bounces off, goes to your eye, and then you see it as being orange. If the beta carotene didn't absorb anything, then carrots would look white because sunlight is white light. So could you use beta carotene as sunblock? Yes, you could. I think Lady Gaga has tried that before, some of her outfits in her early days. So what about the chemical properties of alkenes and alkynes? Well, I split this up into two categories: addition of symmetrical reagents, and then addition of unsymmetrical or asymmetrical reagents. So the first one is hydrogenation. So what we're going to do is we're going to go from an unsaturated bond to a saturated bond. So the hydrogen, one hydrogen goes here and the other hydrogen goes there. Alkynes are going to require 4 equivalents of hydrogen. So it has to go one here, one here, one here, and one here. Okay. And you might be wondering, what does the catalyst do? The catalyst is rather interesting because it doesn't seem like this would happen, but it does. If you take a really nice shiny metal surface, metals want to donate electrons. They easily give up their electrons. So here's a hydrogen, it bumps into it, and it starts sharing electrons with this electron-rich metal down here. So you've essentially broken the hydrogen bond, which is not unusually strong, but it's a stable bond because the electronegativity difference is 0. So now you've loaded up the surface of this metal, and whenever one of these triple bonds or double bonds bumps into it, it says, hey, let's get together and become saturated. And this is exactly what they do with vegetable oil. So again, vegetable oil has these cis double bonds, right? And by the way, this fatty acid right here, the last carbon is called the omega carbon. So this is omega 1, 2, 3. That is not an omega-3 fatty acid. It's an omega 1, 2, 3, 4. But you can see where omega-3 fatty acids come into play, right? So if I'm going to saturate this all the way, I'm going to need 1, 2, 3, 4, 5 equivalents of hydrogen. Okay. So this is a liquid, so it's called an oil. If I stiffen it up like this, it becomes a solid, so it now becomes a fat. So how do you make margarine? You partially hydrogenate it until you get to the right consistency that you want. And what would it look like? It would look like if you took oil and put it in your freezer, it would look like Crisco, be kind of a whitish, disgusting looking solid. So you have to make it look yellowy like butter. So you add some carotene, you add some salt and some butyric acid for flavor. And yeah, so you increase the number of London's attractions and make it into a solid. So here's the partial reduction of alkynes. Okay. And so by poison catalyst. So here's the issue that the early chemists had to deal with. If double bonds and triple bonds were the same, I should be able to take a triple bond and stop it at a double bond. But they couldn't do that. They couldn't find a way to do it because both of these were able to come in here and fully get saturated. It would just go all the way to the point of saturation. So somebody decided, let's not use a pure catalyst, let's muck it all up. So they called it a poison catalyst. And so then you have other molecules contaminating the surface of this. So it allows the alkene to get close enough to get two hydrogens, but the alkene cannot. Okay. So they were able to finally show that you can take a triple bond and stop it at a double bond. And then we have halogenation. So bromine is a reddish-brown solution. So if I take a reddish-brown solution and I put a drop of it into an alkene, it kind of makes that red color go away. Because what's happening is that one bromine is going here, the other bromine is going there. And alkynes would require 2 moles of halogen, right? Because I need 1, 2, 3, 4 atoms of bromine or hydrogen to go there. But you see, it doesn't matter because bromine and bromine are the same, so it doesn't matter which goes to which carbon. I get the same product. But what if you have an asymmetrical reagent? Then it's not going to be the case. So in this situation, this carbon has 2 hydrogens. This carbon has only 1 hydrogen. These 2 carbons right now are different. And the 2 addition atoms are also different. This is an asymmetrical addition reagent. So now if I'm looking at the hydrogen, and here's the reason why I would be looking at the hydrogen. Bromine has an atomic mass of about 80. Well, this is about 1. So this thing is huge. This thing is tiny. Which one is more easily going to get to that carbon? Well, it's going to be the hydrogen. So that's why I'm leading with the hydrogen. So if I put the hydrogen here, right, where's the bromine going to go? It has to go here. Okay, so that's 1. But what if I would have put the hydrogen over here? Then the bromine would have to go over there. Now, are they the same molecule? Here is a 2 bromo. Here is a 1 bromo. They're different, aren't they? So Markovnikov's rule, this basically is a way to say, well, which product is going to be the major product and which product is going to be the minor product. And it's not like this is 99, this is 1. This could be 51% and that 49%. But Markovnikov's rule almost always works. So what it really says is that the rich get richer. The rich mean the more hydrogens you have bonded to the carbon, the richer the carbon is. So this carbon has 2, this has only 1. So this green one is the richest carbon, it's going to get richer. That means that this is the major product. Sometimes it's called Markovnikov's product. And alkynes require 2 moles of hydrogen halide. So again, this one has 1 hydrogen, this one has none. Okay. So this is the richest, so it's going to get richer. So this is the intermediate over here, right? And then I'm looking at it again. Well, if I'm going to put another hydrogen on there, where's it going to go? This one has 2, this one has none. So again, I get this as my major product. You will get minor products. I didn't bother to put them. So I don't want to spend time on reaction mechanisms. And here's the reason why. Organic chemists have finally figured this out. Said the reaction mechanism that you do in the test tube is not the same reaction mechanism that happens on the surface of a protein or any other catalyst, by the way. But if we were doing this in a test tube, then we would go through a carbocation mechanism. So, first of all, I'm leading with the hydrogen simply because it's so much smaller. Okay. And so here's kind of what's happening. Here's the bromine, and it's going to follow up with either going here or here. Okay. So why am I saying that this is a secondary carbocation? With a positive charge right there, that carbon has 1, 2 other carbons bonded to it. This one over here has only 1 carbon bonded to it. Now the predominant feature on a carbocation is that full positive charge. What can I do to reduce the magnitude of that full charge? I need to donate electrons to it. So who can donate more electrons? Hydrogen or carbon? Obviously carbon. So I have electrons being donated from that carbon and from that carbon. Here I have only from 1 carbon. So that means that a secondary carbocation is more stable than secondary carbocation. I mean a primary carbocation. And they use the term hyperconjugation, and then to do that we have to draw pi orbitals and do all this kind of stuff, but we don't care about that because it's not that important to us. All we really need to know how to do is apply Markovnikov's rule. But these are in the transition state. So here's what happens. Here's the potential energy of your products. Here's some of your reactants. Here's the potential energy of your products. What does it take to get there? In the transition state, which is the highest energy in that mechanism from going from reactants into products, why is the primary carbocation such a higher energy compared to the secondary? Because the secondary is stabilized by hyperconjugation. So if I can control the temperature correctly, I can make it so that I have enough energy to overcome this activation barrier, but not this one. So at a certain lower temperature, I can really control this reaction to get a lot of this formed, going through the secondary carbocation. If the temperature is just really radically hot, then this difference won't make much of a difference. So we're looking at Markovnikov's rule. If there was an enzyme that governed how this reaction went, to catalyze this reaction, we would not get two products. We would get only one product. The cell does not have time or energy to say, oh, well, I made some of this, but now what do I do with all this junk stuff I don't need? It's going to muck up everything. So what that means is that what does an enzyme do? It controls what happens in the transition state by changing how the transition state works. Anyway, so here's another one, addition of water, called hydration. So you might think of water as this, and then you can see that it's an asymmetrical addition reagent. So the hydrogen could go there, or the hydrogen could go there, and you will get both products. But where is it going to go primarily? This carbon has two hydrogen, this carbon has only one. So this is the richest. It's going to get richer. So I put the hydrogen here, the hydroxy has to go there. So this is my major product, my Markovnikov's product. And alkynes require 2 moles of water, right? And again, you use Markovnikov's rule twice, essentially. So, another one is polymerization of alkenes into plastics. Okay. So, I put this in a red box. It's a reaction mechanism, but it's really nice to see that we can do 2 of the major reaction mechanisms right here. Carbocation is an intermediate, or a radical is an intermediate. So I'm simply going to go through radical polymerization of alkenes. So first we need initiation. Here's hydrogen peroxide. Hydrogen peroxide and other peroxides can undergo 2 types of reactions. One, it just basically turns into water and hydrogen. And the other one is a homolytic cleavage. Homolytic cleavage is unusual. It doesn't happen very often, but the 2 electrons in a covalent bond basically go in opposite directions. When you do that, you get 2 radicals, 2 hydroxy radicals. What is a radical? Anything with an odd number of electrons. So both of these have an odd number of electrons. And why do we call them radicals? Because they're just extremely reactive. They want more than anything to get their electrons paired up again. Again, how many electrons are in an orbital? 2. What makes an element more stable? All of their orbitals either completely empty or completely full. And if they're completely full, then every orbital has 2 electrons in it that are paired. That's what these 2 radicals want. So this radical bumps into an alkene monomer. And what happens? It forms a bond. I take this pi bond right here. 1 electron goes this way to interact with that electron right there, forming that new bond, quenching that radical. But then the other electron has to go this way. Oh my God, now this becomes a radical. I've turned one of the monomers into a radical. This was the catalyst. this is what's called the initiating molecule, but it was initiated and formed because of the catalyst. So then I got a whole bunch of these monomers hanging out, but one of them is super reactive. So look what happens. This interacts with one of those pi electrons, makes the new bond here, and that goes off and forms another radical on that end over there. And after a while, this one hydroxyl group is not even important anymore. It gets drowned out in the millage of radicals, and you essentially get polymers that can grow on both ends. Okay. So this is propagation. They simply add, and the polymers are getting longer and longer and longer. Then at some point, you get termination. In termination, two radicals quench each other. So here I have a radical, and here's another radical, right? What happens when these two come up against each other? Well, they can form a covalent bond. The radical is gone. Another way to quench a radical or cause termination is to simply put a reducing agent in there. Reducing agents that supply electrons, usually in the form of hydrogen atoms, right? Here's how I quench that other side right there. Okay. So you might want to know of the different steps in free radical, but I'm not going to ask you to draw anything or anything like that. Okay. So polymers can be formed into hard solids, elastomers, foams, fibers. Some of the recycling codes. Let's see if I can find this now. Come on. So here's ethylene, okay, is the monomer. So what can we do with ethylene? Well, we can make polyethylene, also known as polythene, also known as PET, also known as high density polyethylene. So these are containers, low density polyethylene are used in packaging. Here's the recycle codes, right? So in Hawaii, we recycle really only 1 and 2. These are the only ones we really recycle. So PET and high density PE is all we recycle. I look at what people throw in the blue bins. They're absolute, they don't give a damn what they throw in there. They just throw anything in there. I don't even know how we're doing recycling because somebody at the recycling place has to separate out all the 1s and 2s from all the other stuff. So notice that if I replace one of the hydrogens with a chlorine, I now get vinyl chloride. The word vinyl comes from, if you have anything sticking onto a carbon that's involved in the double bond, that's called the vinyl position. So these are vinyl hydrogens. These are vinyl hydrogens. This is a vinyl chloride. Okay. So PVC, tubing, construction stuff. Here's 1,2-dichloro ethylene. And yeah, also known as PVC, but that's saran wrap. Okay. Here I put a vinyl methyl group on there, also called propylene. So polypropylene. Here's styrene. Here's Teflon. Okay. Here's acrylonitrile to make Orlon, acrylics, stuff like that. Here's ethyl acrylate, which is latex paint. Here's methyl acrylate, which is lucite, plexiglass, glass substitutes. So polytetrachloroethylene, also called Teflon, was invented in 1938. And anyway, it was really interesting how everything worked out. It was basically discovered by accident. And I heard a story from one of my organic professors way back that they found this substance and it couldn't be dissolved with anything. It couldn't be stained with anything. So somebody said, let's make it into clothes. So they spent all this time figuring out how to weave it into cloth, and then they made a pair of pants out of it. Somebody puts it on and they're throwing things on the pants. Look, nothing stains it. Everything just falls off of it. And he goes to sit down in a chair and he just like slipped right off. Don't know whether it's true or not. But it was part of the invention that helped America get the atomic bomb first. That's what ended the World War II. It was also used in the production of jet engines. And yeah, so in 1954, there's a Tefal brand made in France originally. They were called Happy Pans. Yeah. So apparently Teflon is the only substance that geckos can't stick to. Anyway. So what should you be able to do with this type of reaction? I think you should be able to take the monomer and turn it into the polymer. How do you do that? Well, each monomer has 2 carbons in a row that are going to join. Okay? So if I got 7 of these, I'm going to have 14 carbons in a row. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Then this is going to have just hydrogens on it. This is going to have a chlorine. See how that chlorine just repeats itself like that? What if I gave you the hexamer and I asked you to draw the monomer? All you have to do is find one repeating unit of this. Like for example, this. That's the repeating unit. So I pulled it out and then I know there was a double bond there to start with. When it comes to natural rubber, then it's a little bit more difficult because it's a diene. So I wouldn't ask you to do this. That's why I put it in a red box. But latex is the milky sap, comes from the rubber tree. It then coagulates in air. And what put together latex? It was not something random that happened in a test tube. It was directed by an enzyme. So latex is created by enzymes in the rubber trees. So it's this gooey stuff. It never really gets hard. And then Charles Goodyear, from Goodyear Tires, invented the process called vulcanation, where he used sulfur to cross-link the polymers to make them much more stable, okay? Anyway, So yeah, that gave us tires. Without this, we wouldn't have tires. So then synthetic rubber is made from replacing the methyl group here with a chlorine. And again, it's difficult to draw the trimer or anything, polymer, because there's two double bonds, right? So I wouldn't ask you to do that. Okay, anyway. So what about styrene? So being a surfer all my life, I remember as a kid repairing surfboards all the time. And the resin was always called polyester resin. Then I became a chemist and I'm like, polyester resin, what the heck are they doing there? So styrene is the monomer that's in surfboard resin. The other monomers are there already. They're short little fibers that are floating around in the solution of styrene. So what you're trying to do is simply, when you put the catalyst in there, you're taking these monomers and polymerizing it, and that locks the other polyester ones all together. So you get something that's rather light, can be very strong even when thin, and especially it's flexible when you make it thin and impregnate it with something that helps it stay, keep from breaking, which is your fiberglass. So all you have to do is like, well, what is the repeating unit over here? This would be the repeating unit, right? So you just pull it out, and then you got to put a double bond in there somewhere. That's it. If I had to figure out what the monomer is from this polymer, what is any repeating unit in here? So I take out a repeating unit, just pull it out and put a double bond between it. That's the monomer. Okay. So you may have heard of bioplastics. They use polylactic acid as a bioplastic. They claim that it's compostable. I remember a couple of years ago, I took some of this and I put it outside under a rock, and I kept watching it for a couple of years, waiting for it to decompose, and it really never did decompose. So what they have to say now is they call it industrial composting, meaning that you need special microbes with their enzymes to break it down, heat, and oxygen to grow the microbes. Then it will break down. And then, this is the last one, I think, for unsaturated bonds, is ozonolysis. So this is ozone. Ozone is O3. And all you need to know is that this goes in here and breaks that double bond. I have 3 oxygens. I need one to go here, one to go here. See that? And then, what is the product going to be? What happens to the ozone? Ozone is more reactive than oxygen. You end up making oxygen. Okay? So this is an oxidative process. And please don't believe that you're going to take a double bond and break 2 bonds at the same time. It's not going to happen. So there's a multi-step mechanism where 1 bond is broken at a time. You form these cyclic intermediates and all that kind of stuff. But all we need to know is that you can take an unsaturated bond and oxidize it. And in chapter 25, we will learn about aldehydes and ketones. This is an aldehyde because you have this carbon double bond to oxygen and then hydrogen. Same here. Okay. So here's another example over here. So questions about any of these reactions over here? It's not. Anyway, what about aromatic compounds? So if I look at benzene, for example, I can draw two resonance structures, right? So I could put the double bond here. And if I just see, because in a reaction mechanism, what you're going to find is that electrons, when they move from one point to another, they chase the other electrons around. So that arrow means that you have two electrons moving in this direction and pushes those electrons that way and those electrons that way. But we get two resonance structures. And sometimes they will draw the benzene structure like this. It's simple to draw, and it emphasizes an important fact. These do not act like double bonds. Unless you got extreme conditions, you cannot add reagents to the double bond. Doesn't work. That's why this structure is sometimes used. So when they looked at benzene, they found that all the bonds were identical. You didn't have a short double bond and then a longer single bond. They were all identical. They also found that benzene is flat and the bond angles were 120 degrees. You can see that each central carbon atom has 1, 2, 3 regions of electron density. So planar trigonal, 120 degrees. Addition reactions don't happen. And so the unusually stable carbon-to-carbon bonds were attributed to resonance stabilization energy. So anyway, we'll look at that in a second. So the 6 pi electrons, 2, 4, 6, right, the ones in the double bonds, are delocalized. They can actually form a ring current. So what that means, with a double, single, that's conjugated, right? Let's look at what this double bond means. First, there's a single bond between the two carbons. What is the double bond? Well, in carbon, there's a leftover p orbital. And each of these leftover p orbitals then start to merge into each other, and you make a system where these pi electrons can exist here and here. But if you look at this, they can move around, meaning that they're delocalized. So what that means, if I start pushing the electrons this way, I just create electrical current. A moving electrical field creates a magnetic field. So we call these delocalized electrons. The electrons can occupy any one of these p orbitals. They're not stuck anywhere. So does benzene absorb light? Yes, in the ultraviolet range, it certainly does. So how do we name substituted benzenes? So we could call this methylbenzene, but you should know the name toluene because toluene is accepted by IUPAC. We could call this hydroxybenzene, but we also need to know its name is phenol. This would be aniline. This would be called benzaldehyde. This would be called benzoic acid. So right now, you really need to only know toluene. When we get to the chapter on alcohols, then you would have to know this. When we get to the chapter on amines, then you'd have to know this one. See how that works? I'm not telling you to memorize all these all at once. Then naming multi-substituted benzenes. So this would be called 2-chlorotoluene. See how this is already toluene? So you took toluene and you put a chlorine atom on it. That'll be carbon number 1, that'll be carbon number 2. This will be called phenol. But what did you do to phenol? You put 3 chlorines on it. So the numbering system would be 2, 3, 4, and 5, right? So 2, 3, 5 is a lower numbering system than going the other way. And then there's an older system that is still in very common usage. And that's using ortho, meta, and para. So it's really only used when you have 2 substituents. So we could say 1,2-dichloro, or we could say ortho. Ortho is when they're right next to each other. Ortho is also used to describe a position. So here's this carbon atom, ortho to that. In other words, right next to it, that one or that one is another substituent. If I skip one, it's called meta. So this is the meta position relative to that chlorine. This is the meta position. And this is the para position, exact opposite sides. Okay. So this would be called para-chlorotoluene. You could also say 1, 2, 3, 4, 4-chlorotoluene. So orthochlorophenol, metachlorobenzaldehyde when we get to it. So biphenyls and polyaromatic hydrocarbons. So biphenyls are 2 phenyl groups, 2 benzene groups. Okay? So phenyl is another name for benzene. If I have it just by itself, it's called benzene. So I could say that this would be called phenyl benzene, or we just say biphenyl. So if I start putting chlorines on here, then they're called polychlorinated biphenyls, PCBs. PCBs are very stable. They have important purposes in industry, in the transformers of electricity. But they're so stable, they start to accumulate especially in mammals. Marine mammals especially, they've found a lot of biphenyls in them. And here's naphthalene. Notice that biphenyls are 2 separate benzene rings, where naphthalene is not. The rings are fused. You do not have 6 and 6, in other words, 12 carbons, you have only 10. And then we have the polyaromatic hydrocarbons. So here's naphthalene. There's all kinds of different ones like this. These are often found in soot and stuff like that from burning or incomplete burning of fossil fuels. And again, they're not good for the environment. None of these are good for the environment, especially if you put chlorines on them. So the physical properties of aromatic compounds, similar to all the hydrocarbons. There's no polar bonds, so it's only London's attractions, nothing else. Okay. So I guess we could rush through the chemical properties. It's an online class, so you're supposed to spend a lot of time at home, online. So we don't have addition reactions. We have instead substitution reactions. And so I put all these in the same number, aromatic substitution. So halogenation, we replace a hydrogen with a chlorine. Alkylation, notice that this is an alkyl group. I take off a hydrogen from here, combine with the bromine, and now that alkyl group needs somewhere to go, so it goes to that carbon. Okay. Acylation. So this right here is the acyl group. This is the alkyl group. This is the acyl group. So again, you're making a small molecule, simple molecule. Now that carbon needs another place to go, so it goes to replace where the hydrogen was, since the hydrogen was taken away by the bromine. Nitration, you can think of nitric acid like this. So if you do that, the hydrogen gets taken off and forms a water molecule. And now that nitro group is going to go back there and form that fourth bond for that, or the third bond for that carbon, or the fourth bond, one of them being a double bond. So you get nitrobenzene. Sulfonation, again, take sulfuric acid and think of it like this. So again, you're making a small molecule that's going to be rather stable, whether it's water or whether it's a hydrogen bromide or chloride or something. Now, that sulfur needs one more place to go, right? And that carbon needs one more bond, so you let them have it. Okay. So in some cases, you'll see benzene sulfonic acid like this. I get really upset when I see that because they're giving sulfur 2, 4, 6, 8, 10, 12 valence electrons around it is in violation of the octet rule. If you do it this way, you don't have to violate the octet rule. Okay. So anyway, get it? I'm dying after the exam. Save me, I'm dying. I'm trying. Yeah. So what do you guys feel about Vladimir Putin? He's a dictator, isn't he? Trying to make himself a lifetime president. That's a dictator. So any questions about any of chapter 22? Because we just finished chapter 22. Any questions?
No.
So you're learning that organic chemistry goes pretty quick, doesn't it? This course goes pretty quick. That's life. So anyway, tomorrow I have my system meeting, so we'll continue into chapter 23 about 1:30. Sound good? So meanwhile, you guys have a great day.
Thank
Thank you.
you. See you tomorrow.
Thank you. Take care.